Oh, hello there, everybody. We are going to continue on with our PChem lectures. So we've just talked about the, the second law of thermodynamics, which pertains to heat and work. Now we are going to talk about, we just did, that's the first law of thermodynamics, heat and work. We just talked about entropy always increases, right, which drives the expansion of the universe and other properties such as gaseous mixing. Now we're going to proceed on to the third law of thermodynamics. And the third law of thermodynamics has to do with the idea of absolute zero. So there is such a thing as absolute zero, the coldest temperature, and that means at a point all motion ceases. And here we're going to talk about what happens when temperature happens. So very cold temperatures and very hot temperatures. Third law, thermodynamics. Let's do it. Usual thing, I'll turn off the video so you'll have a full screen view. And let me share the screen. Oh, this time, hold on one sec. Let's put that down, put this down. And here we are from the lessons from the last time. So we're gonna have a new page, 14th lecture. Now we cannot make a title. Lecture 14. Entropy and the third law. All right, let me switch over to the pen mode and we are good to go. All right, entropy increases with temperature. This should have been fairly obvious from last time. Entropy, usual pen color. Entropy increases with an increase in temperature. So, like we were saying, we have du equals dq rev plus dw rev, right? This is the first law. We have done ds is greater than or equal to 0. This is the second law. And now S at 0 Kelvin equals 0. That's the 0 Kelvin, not okay. This is the third of thermo. And the key thing that will come out of this is that it provides a scale for entropy. That means that there is such thing as an absolute temperature, right? We can reference it to that 0 Kelvin, and then they were always saying how much entropy we have in relation to that amount. And so this is why it will be so important. So every substance has a finite positive entropy. And that's because it's not frozen solid, right? It's not a crystalline thing, right? So biomolecules have quite a lot of entropy actually. At 0 Kelvin, the entropy may become 0. Perfectly crystalline substances do have 0 entropy. Probably a hypothetical. at 0 Kelvin. So this means that we have a starting point to the temperature scale. This establishes S sub 0 value for delta S. In other words, it's a change from something, but what's it a change from? Well, it's the reference point, and that's 0 Kelvin. So this means that, well, the Kelvin scale, unlike other temperature scales such as Fahrenheit and Celsius, it has a meaning to what it is to be 0. I mean, the other ones have some meaning, but it doesn't mean there isn't any heat, right? And so we have a more precise meaning of what that is rooted in thermodynamics for the Kelvin scale, which does not exist for other temperature scales. And this is why certain formulas call for the use of Kelvin and not the other temperature scales. So we want to take a look at this from the multiplicity point of view. Okay. Let's think about configurations of molecules. So we're back to KBLNW. Right, this is entropy. Configurations of molecules. At absolute 0, all the configurations will be at there's only one conformation accessible. So in other words, if these were proteins, they would, lattice proteins, remember we did the lattice proteins, they would all be folded. And you remember how we talked about the distribution of the protein conformations over different temperatures, very hot temperatures, thermodynamically speaking, medium and cold temperatures. The idea here is very similar, and this provides us with some insight into this. So here we have a collection of lattice proteins. Oops. Thinks I'm scribbling and deletes it. All proteins are folded. In the lab, when you have a colder temperature, what do you do to keep your proteins from unfolding? You put them on ice. Well, why? Because when it's colder, there's less entropy and they stay folded. S at 0K equals positive equals KB ln of 1, because there's what's ln 1? I think there's a minus sign here. There is one way to arrange the system. Folded. This kind of assumes that the lowest energy state is the folded state of a protein, which is not always the case. But for lattice proteins, we have this nice observation. Okay, so this means the entropy is 0. So any configuration system not at absolute 0 will have a higher entropy, which is basically the second law, right? So any implication system not at absolute zero pretty much all the time. Right, delta S is greater than zero. The third law from probability perspective can be written like this. All right, so we would write it something like this. S is negative KB sum over J. Pj ln Pj, which is the probability Pj equals prob to find system in state J. At absolute zero, only the lowest energy state is occupied. We kind of already knew that. Just a few words there. At absolute zero, only the lowest energy state is occupied. In other words, we'd have P0 equals 100%. 100%. And P sub J is not equal to zero, equals zero. J not zero, right? So the PJ is 1, which is 100%, and any other choice has no options, right? That's what this says. It says they are all in the ground state. S equals negative KB summation from 1 to infinity is equal to PJ ln PJ, accountable for all the states, equals, there's one state. Okay, S equals negative KB sum from 1 to infinity, 1, oops, this 1 ln 1 ln 1. Substitute in your values. And guess what? What's ln of 1? Remember that's 0. So this whole thing equals 0. In this viewpoint, we see that the entropy at absolute zero equals 0. This, of course, is not a great overview of all of this, because this is a bit of a hypothetical situation to an idealized situation. Are there things that actually behave like this? Possibly, but you're not really going to get normal substances. They're perfect lattice crystalline state. That's the thing. All right, so because of absolute zero, we can declare the lower bounds on T and on entropy, right? So we have a reference point. So entropy as a function of T is given by the following. Entropy S of T function equals. I'm going to run from T1 up to T2. C sub B of T over T T. So in other words, the entropy is related to the heat capacity. Now we can substitute in the absolute zero. And so what we can do then is we have entropy now has established what the initial temperature is. Right? It begins at zero. The heat capacity as a function of T over T dt. So in other words, we can establish where the beginning of this is. It's absolute zero. So what we did here is we set the entropy scale, right? So it's now at an absolute scale. And the entropy S is measured relative to entropy at absolute zero. So in other words, entropy and temperature are quite integrally linked. Okay. There are a number of partial derivatives of entropy and corresponding integrals that are useful for heat capacity. So I'd like to provide you with this little table, which I think you will find helpful. Useful partial derivatives. As opposed to unuseful ones. And some corresponding integrals for heat capacity. All right, so I'm gonna divide it up according to the different situations. So we have constant volume, constant pressure, and constant temperature. So we're gonna start with the constant volume one. So I'm just gonna put some guidelines for myself in here. Sometimes this thing realizes that I want to make straight lines, and sometimes it doesn't get that. Okay. Constant volume is the first one that we want to do. All right. So ds, the change in entropy with respect to the temperature while holding volume constant, right? So this is a partial derivative again because we have the constant volume equals C sub V over T. Now, something out to you. Okay, so this is V for constant. This is volume is constant. And this also means volume is constant, right? C sub V. And here is the partial derivative with volume constant, right? So it's under the constant volume situation here. And the corresponding is this entropy equals T1 to T2 C sub V over T dt. And this is the constant volume. Right. Now we have the pressure version of this. So now we're going to look at the entropy with respect to pressure, and we will hold. No, that's not right. Can't do that. It's either one or the other, right? This is a T. The entropy with respect to temperature at constant pressure, that makes more sense, equals C sub P of T over T. Okay, so now we have C sub P. Right? Notice this means constant pressure, and here's the heat capacity at constant pressure as a function of T, right? Okay. What is the entropy? In this case, the entropy is equal to T1 to T2 . We could also write this as a function of temperature. This is just, I didn't make it look like an equation, a function. This is just function notation, right? It doesn't actually change anything. It just says constant volume is a function of temperature, which we can already tell from this integral limits. All right, here's our integral limits. Now we're going to do C sub P of T over T dt. Oops, not little t, big T. Big T, big T, it matters. At constant pressure. All right, and now, what do you suppose we will do next? Which one did we miss? Temperature. Okay, so now we're gonna write another equation. Okay, this one will be a little more complicated because there's not a heat capacity for this one. This one will be ds dV with the temperature constant equals, ready, 1 over T times pressure plus du dV, the internal energy with constant temperature. Now, interesting fun fact. It's constant temperature. So the integral of T1 to T2 wouldn't actually be over anything. So there's no area under the curve. Right, because it would be the same. So there's no entry here. Okay, so that's our little table of formulas, which I've organized for you. Let's see. Yeah, not too bad. All right, I'm just gonna also put like a little line here. So hopefully that makes sense to you. All right, good. Next, we have absolute entropies of gases, and these can be calculated from partition functions. Those partition functions continually have more and more uses for us every day. Absolute entropies. So what is the relationship between entropy and the partition function? Let's find out. S equals N KB plus N KB LN Q VNT over N. What's this big N? This is the number of particles. Plus N QBT. Dear, running out of space. TLNQ. That does not look right. Let's do it like this. TLNQ over DT sub B. All right, we have a few things to annotate here. This capital N is the number of particles in a macroscopic system. And yeah, this could be a little bit confusing. Remember that we had Q plus W for heat and work, but we also had Q for the partition function. This is the microscopic partition function, not heat. This is microscopic. very important. The meaning would be quite a bit different. Okay. This is a note about Q. The question then becomes what to use for Q. How should we represent partition function? We have a couple of choices. System partition. Okay, remember this one. U of NVT equals sum of J. Remember this stuff, the exponentials, E, the negative EJ over KBT. However, this is not appropriate. For the individual gases. So what we're going to do is we're going to make use of the formulas which we derived before from the previous chapters. The monatomic, diatomic, or polyatomic. Gases from the previous lecture to account for specific gases. Remember we had partition functions. It was the second lecture in our series of partition function discussions at the very beginning of part 2 of the lecture series, right after we completed quantum mechanics. I think it was the second lecture after that where we covered exactly this, deriving as other partition functions for the gases. So let's just write a quick summary of what we learned from those. You know which ones I mean here. I might be able to just bring it up for a sec. It was particle in the box, ideal, anneal, Boltzmann ensemble, partition function, and the ideal gases. I think it's this one. Let's just switch over to here for a sec, just to do a quick review. All right, remember we wrote these partition functions, and we talked about the Riemann sums, translation energies, electron. Yeah, these ones. Okay, remember that we had looked at these partition functions. So here's an electronic partition function. Here's so that was for the monatomic gas, right? Here's your diatomic gas. So you have this partition function for the diatomic gas. Well, we have the total energy, right? This was the electronic part, and then we did, no, this one's electronic, this is the translational part. Then we did the vibrational part, and then we did the rotational part. got this equation, and then we looked at the average energy, right? So we had all these different parts be put together. So you could pick whichever of these you want. And also for the rotational, notice that you would switch out what you would put in for the various shapes of the molecules. So this is exactly what we're talking about, about putting Q's into the equation, right? You pick which Q you're talking about and you substitute it in. And that's how that is going to work. So let's come back to today's lecture. From the previous lecture. You must select the appropriate Q for your system of interest. For the type of gas you have. Yeah, the crux of the problem is looking up all the constants. So if you actually do problem solving with these, it's a lot about looking things up in the table. And pushing the calculation. We get the final number. I remember a homework problem I assigned on this. Yeah. Yeah, there is a homework problem on H2 that we could consider doing. All right, which illustrates exactly that. It's a very long problem, but it's not difficult. It's just substituting things in. All right, so let's take a look at trends in molar entropies next. Yeah, so in other words, n is constant, right? Same number of particles. And we got to consider this situation. The entropy of a gas is greater than the entropy of a liquid, which is greater than the what? Entropy of the solid, right? So in other words, this is the least ordered, and this is the most ordered. Right, so you have the greatest entropy here. This has the least entropy. So, but why does this happen? Due to the level of translational freedom. This totally applies to biomolecules about them moving around. Okay, so if you do not have the ability to translate, like you're in a solid, like an ice cube, then there's not going to be a whole lot of moving around with the particles. So the entropy is going to be the lowest And this is going to be the most ordered system. That's why you can take an ice cube out of a tray and hold it in your hand, right? The molecules are very ordered. They stick together and have a shape all by themselves. But it's not going to work with a gas or with a liquid. Gas particles translate in 3D and have few interactions. Solids at the other extreme. Particles are gonna interact strongly. By hydrogen bonds, for example. And they don't translate much. Liquids are in the middle. And they have more or less fixed volume. I'll just put approximately in parentheses. Liquids we are not readily compressible, resulting from intermolecular interactions. Right, so water does have hydrogen bonds, but not as many as ice. All right, so now let's talk about size. The entropy of a large mass is greater than the entropy of a small mass. Why? Well, it has to do with the number of slots that you have, right? You think about those chambers, right? So there's more slots, there's more combinatorics. Larger mass corresponds to greater thermal disorder. More translational energy are available. This leads to greater entropy. Okay, let's do another comparison. The entropy of more atoms is greater than the entropy of less atoms. So the more atoms in a molecule, there's weird stuff sometimes. Greater the ability to take up energy. So if you have more atoms, you'd have more ways to vibrate. So it's more pairs and so on the divisors and pairs each other. So for example, we could arrange, so in order of entropy, here's some molecular structures. CH2Cl2, CHCl3, CH3Cl. So what we notice about this is the number of atoms is the same. And the phase is the same. They differ in mass because there's different atoms. So greater mass corresponds to greater entropy. So we just order the mass from greatest to least. All right. So we could then write the entropy. Wait, that's not right. CH3. Then we'll have it's C8. No, that's not a legitimate formula. What's going on here? It would be CHCl3 is greater than the entropy of CH2Cl2, right? Which is greater than the entropy of CH3Cl. And so this has the greatest. CH3Cl3 does not exist. Okay, this is correct though. This is CH1, right? So because chlorine weighs more than hydrogen, that's why this is the right order, right? The more flexible the molecule, what do you think? The more flexible the molecule, the more entropy. It has, okay. So here's an acetone. C3H6O acetone. But we could use the same building blocks and make something else. CH2. This is also C3H6 246 6O. Now, this is more flexible because it's got rotable bonds. This doesn't have rotable bonds. This is rigid, not rotable. So what do you think? This has greater entropy. This has less entropy. Okay, let's talk about residual entropy. So the values of entropy can be experimentally measured with the calorimeter. Most are in excellent agreement with the calculated values. There are some which do not agree. What type of molecule and why do these values not agree? How can these be reconciled? All right, so most values agree to calculated, some do not. What's going on here? Which ones are susceptible to this problem and why? Well, that's what we're about to find out. So the answer is molecules with small dipole are problematic. Why is that true? Consider carbon monoxide weak dipole. So the entropy calculated equals 160.3 joules per Kelvin mole. And the entropy experimental equals 155.6 joule per Kelvin mole. Not equal. What's up? This is the calculated is greater than the experimental, and the delta S is equal to 4.7 joule per Kelvin. That's kind of a lot. What is going on? This difference is the residual entropy. So, what's going on? We're going to need to take a look at the lattice to understand. When you have a perfectly aligned lattice, that's great. But you could have a not perfectly aligned lattice. Probably need some kind of link pattern here, but okay. Here's a perfectly aligned lattice. Here, let me do this. The lattice box. Let's put a lattice box around these. And say that's the unit cell. Not aligned. Okay. How many ways are there to have a perfect lattice? One way to have a perfect lattice. So S equals R L N W. This is the ideal gas constant. S equals R L N W equals oh yeah, wait, oops, forgot. Substitute the number in 1 equals 0, which ln 1 0. So there is no entropy. It's kind of like absolute 0. Here's one that's not aligned. When the dipole is small, a field large enough to be detected by the neighbors is not generated. And by the neighbors, I mean the neighboring dipoles. Dipoles are lying randomly on the lattice. This means there is some inherent motion even at 0 Kelvin. There is some, yeah, I must go here. There is some inherent disorder even at 0 Kelvin. All right, example, let W equal 2. All right, yeah, so the ways to align things are up or down, right? That's what these arrows mean. S equals R ln W. So S equals R ln 2 times 8.314 joule per Kelvin mole ln 2. It's a little sloppy, and I get the comprehensive one. Okay, so S equals 5.76 joule per Kelvin. The entropy obtained from this treatment approximately equals the residual entropy found from calorimetry. So you see why this works. So when you have a strong dipole, you have this situation here, and they're all aligned, so you're able to get a field. But when they're like this, it's mixed, right? And so this is why when you have a molecule like CO, you have the problem that your comparative state is not really that aligned to begin with, and that's what causes the problem. This is D, this deuterium, right? Heavy hydrogen. Right? Sort of like nothing, but one is heavy. Therefore, possible orientations. Right, because you basically have, well, it's the tetrahedral, but I'm going to draw it flat just for the moment. Like, Right, so you're gonna have, could be there. These are, of course, all tetrahedral. I'm just drawing a flat projection. Okay, so there's 4. W equals 4. So S residual equals R ln 4 because of the fourfold symmetry of the system. So the residual entropy depends on the symmetry of the molecule when it has a small dipole. This is an important idea. Residual entropy depends on the symmetry. Right, so this is fourfold. This we have basically nothing. Good. And that actually is one more page I need to get through. All right, awesome. So I think we may actually finish a little bit early today. So let's just review what we talked about today. Today we talked about the third law of thermodynamics. So the entropy is related to the temperature of the system. When the temperature increases, the entropy is greater, which we kind of already knew from the idea that the entropy of the universe is expanding. And so it makes sense that this would follow because gases expand when they're hotter. So if the temperature is increasing, the entropy should increase, which sort of is related to what we talked about last time. And also we have this idea that we have an absolute temperature, right? And so there is like the coldest you could be, 0 Kelvin. And so this is really important in today's lesson because it basically what it does is it establishes the 0 point, an absolute reference point for a scale. So that means that whenever you measure anything in Kelvin, that it's relative to some reference state that means there's no energy. So it's not like other temperature scales. Like if you say the temperature is in Celsius, right, it's telling you relative to the 0 point, but it doesn't mean there's no temperature below 0, because there is a temperature below 0, which means there is thermal motion. But this scale is special because it really is related to these thermodynamic properties. That is the idea that particles move at a temperature. And so that's why that's really important. All right, so we took a look at the multiplicity. So we have our new equation, S equals negative KV ln W. So this is the multiplicity equation. And we were able to look at lattice proteins and see that when we are at cold temperature, that there is only one way to be folded. So this, of course, it applies to real proteins, although it's important to note that real proteins may not always be folded at their lowest energy state. But for a simple protein, that's probably true, and it's mostly true. All right, we also took a look at the third law from the probability perspective. So we were able to see about the multiplicity from probability. So when you don't have different ways to orient things, then it means the probability to be in the only available conformation would be 100%. And so we were able to compute this, and this means that there's 0 entropy because ln1 is 0, ln1 is 0. All right, so then we are also able to write some useful partial derivatives of the entropy. So we worked this out about the change in entropy for temperature, at constant volume, and then we did the corresponding formulas at constant pressure. And finally, we did the constant temperature. Interestingly, when there's no temperature, you don't like have a delta S. There can't be a change in S when there's no change in temperature because you can't take the integral over anything. So V and P both correspond to the partition function. And then we take these corresponding integrals that we worked out, which is how you can calculate that. Okay, also we saw about the absolute entropies of gases, and we saw that we can use the partition functions in order to calculate this. So you just basically have the number of particles and then kBt of the log of the partition function plus kBt times the partial derivative of the partition function to temperature, right? So what you would need to do then is you would need to substitute in what Q you are working with, right? So in previous lectures, we had talked about the various kinds of partition functions that we could write. We could write them for gases, we could write them for a monatomic gas, we could partition it out for the various components, the electronic, the vibrational, and so on. And we can pick which Q we're talking about and substitute in here and compute the entropy for that. All right, we looked at trends in molar entropies, and this very much relates to molecules because there are a lot of qualitative things that we can do here. We can certainly understand that the gas has more entropy than a liquid than a solid because of their states and their ability to translate around. We could also look at it in terms of the masses. So a large mass will be greater than a small mass, and this also will have to do with the number of atoms, which is pretty similar to the mass size. So if you were given a set and they differ in their number of atoms, then having more atoms will be greater than less atoms. And so we did an example here where we arranged the molecules based on their number of different kinds of atoms, and they have different mass. And here we did it in terms of the flexibility. So if you had more flexibility by having rotable bonds, you'd have greater flexibility than if you had something that was stiff, which would not. And then we talked about the residual entropy. So this gets at why at absolute zero, you wouldn't necessarily have the entropy be exactly zero. But the interesting thing is you can actually measure this with calorimetry. And so when you don't have a strong dipole in your system, such as with carbon monoxide, you are gonna have the possibility to have some residual entropy, and this has to do with the non-alignment of the dipoles in the system inherently. And so you can actually measure this by looking at the difference between the experimental and calculated values. And then finally, we took a look at the orientations of lattice type. So the entropy then will depend on the symmetry of the molecules because there are different ways to orient these. All right, well, that's terrific. We'll be moving on to the Gibbs and Helmholtz free energies in our next lecture. So hope you enjoy this, and we will talk to you soon. All right, bye-bye.